All right. Thanks, everybody. Thanks for joining again, the latest installment of the Sustainability Webinar Series. We've got a great presentation from the fun folks at Bldg for Sustainable Materials. They have information today for us about embodied carbon, concrete, and mass timber. Just to remember, for those who are joining, please make sure you're muted while the presenter is speaking. So I will introduce our fabulous speakers today. We've got Megan Fuller. She is a research civil engineer at the Engineer Research and Development Center, Bldg, Construction Engineering Research Laboratory for the U.S. Army Corps of Engineers. She has worked on the Source Reduction and Resource Resilience team with a focus on recycling, composting, and waste reduction. The Sustainable Design and Development team with a focus on leadership and with a focus on lead, let's just do that, and policy, and updates to sustainability guidance and the mitigation of GHG emissions for DoD construction materials and infrastructure project with a focus on environmental product declarations, life cycle assessment, and cost implications of utilizing sustainable materials in military construction to reduce and eliminate greenhouse gas emissions. Her current work includes information and technical support to the Corps reduced and abridged FEMP tool craft with a focus on carbon pollution-free energy, data roadmaps, and extreme weather projects with the Water Use, Resilience, Security, and Technology Group, and the modernization of ProjNet. Ms. Fuller holds a bachelor's and master's of civil engineering from Southern Illinois University, Edwardsville. She previously spent approximately 15 years working in municipal government and as a project superintendent for a construction company. Next, we have Dr. Jerry Paris. He is a research civil engineer in the Geotechnical and Structures Laboratory, where he is an expert in concrete materials, concrete durability, and cement chemistry. In the 1.5 years of service at Bldg, just a second, we're going to make sure everybody's muted here. In the 1.5 years of service at Bldg, he has earned the Civilian Service Achievement Medal, as well as a Program Development Award for his work on bio-based material development for infrastructure. He spent his time at Bldg supporting projects related to biological repair of concrete materials, blast-responsive concrete, incorporation of alternative supplementary cementitious materials to reduce greenhouse gas emissions for civil works and military construction, rapid large-scale emergency repair response for massive structures, and development of nuclear shielding compositions. And finally, we have Talbot Ruppel. He is a research materials engineer for USAID, focused on the procurement, characterization, specification, and implementation of sustainable bio-based building materials like mass timber into military and civil applications. Demonstrated competence in research, design, quality control, continuous improvement, and standard operating procedures alongside colleagues and supervisors. He is recognized as a charismatic, innovative thinker and a meticulous problem solver, fervent for answers, serving as a PIPM, wood scientist, and SME for contingency basing, MILCON, and life cycle assessments, efforts involving said biomaterials. Mr. Ruppel has a bachelor's degree in renewable materials from the University of Idaho, a master's degree in wood science and engineering from Oregon State University, and he earned a post-baccalaureate certificate in construction management from LSU. So with that, I will hand it off to Ms. Fuller.
Okay, mic check, and I'm going to share my screen here.
Yes, ma'am. We hear you loud and clear. Thank you.
All right. Okay, I know we have a lot to cover, so I'm going to jump right in so we can get on to the more fun material-specific items. As Stephanie mentioned, my name's Megan, and I'm going to provide a brief overview on embodied carbon before the others provide a more in-depth look at some specific building materials. In this portion of the presentation, we're going to go through the importance of sustainable materials in construction, a quick lesson on what embodied carbon is and how to assess it, embodied carbon related policy with a focus on some of the latest policy guidance, and a quick look at some lead credits related to lower embodied materials. As recent studies have shown and executive orders have addressed, sustainable construction materials are essential for minimizing environmental impact and promoting a greener future. With a major source of global GHG emissions being from the 4 listed high volume construction materials, there's been a federal focus on tracking, labeling, and reducing embodied emissions in these and other construction materials since Executive Order 14057 was signed into effect. There are many positive impacts to the use of sustainable construction materials because these materials are less resource intensive and more eco-friendly. Their use instead of standard construction materials allows us to take a larger stride toward the path of environmental preservation. If specified correctly, sustainable materials can also contribute to energy efficient buildings by enhancing insulation and allowing for right sizing of HVAC units, which can provide savings in energy and lifetime cost. Indoor air quality improvements occur because sustainable materials emit fewer harmful chemicals and pollutants, which positively impacts the human health and well-being. And finally, sustainable materials can be more durable and require less maintenance, which provides a long-term economic advantage. As I highlighted in green, I'm going to focus on the reduction of negative environmental impacts through these materials, more specifically the reduction of embodied carbon. But before diving into policy impacts, I want to give you a quick overview on embodied carbon. Embodied carbon is essentially the carbon footprint of a material, building, or infrastructure project. It refers to the amount of greenhouse gas emissions associated with the extraction, production, transportation, manufacturing, maintenance, demolition, and recycling of the project, and it includes both upstream and downstream stages of a material's life cycle. You hear the phrase cradle to gate. This is cradle to grave, looking at all of the carbon involved. This is a bit different than operational carbon, which is the emissions associated with building energy use. And operational carbon has been a focus for quite some time, but embodied carbon reductions are relatively new in comparison. In terms of assessing embodied carbon, there are several ways to do so. EPDs, environmental product declarations, are intended to help understand the embodied carbon of a product. Standardization is still being developed, but ideally EPDs will be useful in procurement decisions, either by comparing similar products or comparing that product to a product baseline. That said, product baselines are still also being developed. A little plug here, if you'd like to read more about EPDs, our team did publish a tech note in November of 2023 that has a lot of good information. Second, life cycle assessments calculate the environmental impacts of a product over its span. These can be done on specific materials or can be calculated on a whole building level. The EPA is currently working on a labeling program to make it easier to identify low embodied carbon products. This labeling program would be similar to Energy Star and WaterSense. In terms of accounting for those CO2 emissions, we still need, there's still a lot of work to do. The application of social cost of carbon is probably the ideal solution in order to factor into the decision making. But because these variables are not easily represented in monetary terms, they can often be overshadowed in the cost analysis. As of now, in terms of social cost of carbon, there is not an agreed upon method or value for incorporating that cost. On to federal and Army policy. There are several applicable federal and Army policies related to embodied carbon. EO 14057 was probably a catalyst towards the GHG emissions reductions, and it lays out some specific and lofty goals regarding GHG reduction and sustainability. Per the implementing instructions, all new construction and modernization projects over 25,000 square feet should be using sustainable materials and low embodied carbon materials as determined. Many of the other policies listed on this slide speak to net zero emissions procurement goals as well. But because we have new policy guidance out fresh off from the press in March, I want to focus more specifically on that, being the Department of Army policy guidance on resilient buildings. This policy guidance listed effective immediately for all construction projects other than FSRM. So this is effective immediately for FY27 projects. For FY25 and 26 projects, there is an expectation that proponents evaluate a project for reasonable changes to planning and design to incorporate these efficiencies, unless the cost or project acquisition timeline are impacted in such a way that the completion dates cannot be met. This memo touches on many aspects, including whole building life cycle cost analysis, energy savings, electrification standards, and deep energy retrofits, but I want to highlight that portion that relates directly to our sustainable materials research by focusing on the lower embodied carbon emission building materials as a primary construction material. This policy guidance for lower embodied carbon materials in MILCON indicates that they should be used when available and validated to meet engineering specifications. Regional availability, costs, and impacts on construction timeliness may factor into the use of these materials, but they should be considered as part of the 35% design submittal. Designers should also be requesting and reviewing product-specific EPDs, type 3 specifically, to evaluate and select those materials. The Army currently has specific pilot projects using lower embodied carbon materials, and they do include LCA documentation, EPD tracking, and other sustainability initiatives that will be used to inform the feasibility for use across MILCON. This policy guidance will likely lead to the creation of some new ECBs through USACE headquarters and an update to UFC 1-200-02. More information regarding that will likely be forthcoming. And then finally, for me, before turning things over to Jerry, I wanted to provide a quick overview on LEED with regards to lower embodied carbon materials. I believe there's going to be a more thorough look at LED in a future webinar, LEED in a future webinar, but I will focus only on the materials and resources category. As most, if not all of you probably know, any new or major renovation project requires LEED Silver, and there are several credits directly related to embodied carbon, including EPDs and whole building LCAs that can get your project closer to meeting that LEED Silver requirement. Within the materials and resources category, up to points can be achieved for new construction projects that utilize the whole building life cycle assessment option of the building life cycle impact reduction. And additionally, up to 2 more points are achievable through the EPD's credit. We are also anticipating and tracking that LEED version 5 will further emphasize embodied carbon and building materials. I went through my slides pretty quickly, but now that you have a brief overview of sustainable materials with a focus on embodied carbon, I'm going to hand things over to Jerry, who can give you some more specifics on sustainable concrete.
Great. Let me go ahead and share my screen. All right, can everyone hear me?
Yes, sir, we've got you.
Yep. All right, fantastic. Thank you, Megan. So my name is Jerry Paris. As we said earlier, I'm a research civil engineer. I'm in the concrete and materials branch at Bldg here in Vicksburg, Mississippi. And today I'm going to be discussing the roadmap to net zero concrete. And so essentially what we're going to be talking about is where we're at, what the goals are, so where we're going, and hopefully how we're going to get there. So let's see here. There we go. So as Megan was talking about a little bit earlier, there are some policy drivers that essentially started with the Executive Order 14,057, or the Buy Clean Act. And essentially the main edicts here were the 50% reductions of emissions by 2032, along with a net zero building emissions qualifier by 2045. And so that kind of pushed the tri-services groups to come up with climate implementation plans. And so for the Army climate strategy, they kind of followed the executive order pretty much to a T, with the 50% reductions by 2032 and net zero by 2045. The Navy was similar, but with a net zero by 2050. And then the Air Force climate campaign plan was following the executive order, but shifted by about a year. Following in total with the DoD climate adaptation plan, which has a net zero by 2050. And in general, these on the surface look pretty understandable. Everyone kind of knows what net zero typically means, effectively zero emissions. But the complication here is the 50% reductions, right? As you start digging into that, you start asking the question of 50% reductions of what? And that's a little bit of the nebulous portion here. So if we dive into each one of these climate strategy plans, for the Army climate strategy plan, they dictate that it's from a 2005 year baseline. So 50% reductions from a 2005 portion. The Navy, I wasn't able to find a specific year that they are targeting in their climate action strategy plan. And then in the Air Force was from a 2008 baseline. And what makes this even more confusing is depending on which version of the implementation plan, whether it's the Army climate strategy or the Army installation strategy implementation plan, you may end up getting different year baselines. So what we're seeing here is somewhere in the 2005, 2008 years what we're targeting. But the main issue with any of these target baseline years to go by is that, as far as I'm aware, there's no actual database that tells you what any of these numbers are. So we have to make assumptions on what we're targeting. And so we're still trying to figure that out. So what the industry is doing at this point is saying, okay, we're going to try to make up greenhouse gas limitations. And so this has been done by a couple different groups. GSA has the Inflation Reduction Act for low embodied carbon material requirements, which we'll talk about in a second. The American Concrete Institute has a number of committees related to sustainability, including the most recent one is 323, the Low Carbon Concrete Code Committee, as well as there's other groups such as the Carbon Leadership Forum. And what these all tend to do is prescribe greenhouse gas emissions limits as a function of concrete strength. And so what this generally looks like is you'll usually have a table that will give you emissions limits in terms of kilograms of CO2 per cubic meter as a function of the concrete strength. So if we look back at the Carbon Leadership Forum for 2021, this generally makes sense. If you're looking at it, as the concrete strength goes up, you typically need more cement. So your limits tend to be higher with the higher strengths, and that generally makes sense. And in this document, they noted that they are treating a baseline as a static reference against which to compare progress towards a goal, which is exactly what we want, right? We want a baseline value, right? Because ideally we're going to go back to that 2005, 2008 timeframe. So having some sort of a baseline to work off of is great. And then 2 years later, they produced more baseline values, and they're dramatically lower. And they remove the definition of what they are considering a baseline. And what ends up happening is, for this data set, this baseline is actually representative of a 30% fly ash replacement, or removing 30% of the cement within a concrete and replacing it with a waste material. So that's why these numbers are considerably lower than the data set from 2 years prior. If we look at the GSA values, there are different limits for the top 20 versus top 40 and top 80%. But what you'll notice is that the limitations to meet a top 20 for the GSA limits are actually even lower still. And then we get to the ACI 323 limits. These are draft benchmark values, and you'll notice that for each strength classification, they are considerably lower. And the main reason for that is ACI chose to do it in a different unit. So if you convert from their units of kilograms of CO2 per cubic yard of concrete into per cubic meter of concrete, these are the values that you get. And what you'll notice is that these are very, very similar to the Carbon Leadership Forum 2023 baseline values, that 30% fly ash replacement, because they're working from the exact same data set. So all of these numbers should be very, very similar. So the problem that I foresee with this is that as we start looking at these, they are giving limits, but they're not really explaining how to reach these baseline values. And so in general, there seems to be kind of two ways that they're approaching this. One is letting the industry innovate, just saying that, you know, our concrete and cement producers are just going to have to get better products. And then the second is let the designers, the engineers and the architects figure it out for themselves. And to me, this appears to be a little bit of kicking the can down the road. So ideally, what we are trying to do is we're trying to be the bridge between the gap of what you have to do and how do you actually get there. So what we are trying to do is develop realistic plans. And I've got this as a proposed plan. Nothing is finalized in this, but this is generally what we're working towards currently. If we look at the three different kind of the main sources of limits, ACI 323 provides about 30 pages of specifications, whereas the GSA and the Carbon Leadership Forum can essentially be broken down into, you know, a table or two. And so what our plan is we're going to start with the ACI 323 document because it is the most developed currently. And what their general approach is, they break up the United States by region and choose benchmark values dependent on where you are located, because there is geographic pressure into what you can do and can't do for cement production. So it makes more sense to break it down geographically. And so as we move forward, there needs to be a two-pronged approach, right? Because we have the 50% reduction by 2032, as well as the net zero by 2045, 2050. For the longer term approach, it's a lot more nebulous. Essentially, what we need to do is foster long-term innovations that deviate from known technologies toward net zero emissions. And what I mean by that is, and this is my opinion, is that the current process by which cement is produced, I don't foresee that process being net zero, because if we look at the emissions as a function of Portland cement production, over half of it is coming from a calcination process, where what you end up doing is you take limestone and you heat it up until you drive off the CO2, and you're left with reactive calcium oxide. And that's what that portion is. So if we were to have zero emission fuels and waste emissions today, we would still not be in a net zero process. So in my opinion, I think we need to look at other processes that get away from this calcination in order to meet that large emission drop of the net zero by 2045. But in the short term, there are immediate actions that we can do to meet 50% reductions, and we can do that today. And so that's what my last slide is going to be about, is how we can meet these 50% reductions today. So basically what it comes down to is we need to replace as much Portland cement in the concrete as possible without appreciably impacting the performance. And so what we've been doing is we've been looking at different areas of the UFGS that can be immediately updated to allow more sustainable material choices. And so a couple examples of this are in the UFGS for cast in place concrete. We've just got this approved. It's now in there as of February. We are allowing type 1T cements, which are ternary blended cements. So it's a cement with two replacements that are blended into it. And These have the ability to reduce emissions by up to about 70%. The more realistic case is probably going to be 30 to 50% as they are delivered to the concrete ready mix producer, so that they can do replacements in the field or at the ready mix facility as necessary based on the project. But we can pretty much almost hit those targets today. So those are now allowed in the cast in place spec. We're also debating about including an over design limit. So for structural concrete, in order to guarantee that the vast majority of your concrete meets the minimum design strength, there's an over design. And so what we're thinking about doing is including a limit to how much over design is built into it. So as an example, this is a chart of over 850 production mixes from a ready mix facility. And on the x-axis, what we have is design construction or design concrete strength rather. And on the y-axis is the actual measured strength at 28 days. And in an ideal world, all of these points would line up on this line, right? Your strength that you design is exactly what you get. In reality, concrete's a heterogeneous material, and so we have to include that over design to ensure that the vast majority of the concrete meets that minimum design strength. And so that is through ACI. So the gray line here represents the over design requirement for a given strength class of material. And so you can still see that there's a majority of mixes that are well over this line. And what that means is that it has way more cement in it than what is actually necessary. So if we include an additional 20% over the over design as a theoretical maximum over design, what we find is that these mixes that are shown in red are considerably over designed. So for instance, the mixture is at 3,000 PSI. There's no need to have 8 to 10,000 PSI strength concrete when your design is 3,000. So you would be limiting it to about 5,000 maximum. And that requires the cement loading to reduce. Okay. The other things that we're doing is we want to include materials that are performance-based rather than things like fly ash or slag that have specifications. We want to look at performance qualifying material. And then lastly, and I think this is going to be the big push here, is we're trying to identify regional sources of material that currently meet our specifications, as well as regional materials that might meet our specifications. And what we're attempting to do is locate these different places throughout the US and then take a look at the USACE divisions and kind of overlay them to see where these different materials lie. And then we're going to get these materials in-house and then evaluate them for performance in concrete. And ideally, we're going to take all of the information that we gain and produce region-specific user guides that tell the user in the different regions where are the available sources within their regions, how those different materials can impact the concrete performance, and specifically if there's anything about those materials that dramatically reduce performance. For instance, does a certain cement replacement make the concrete worse in sulfate resistance or worse in freeze-thaw resistance, so that you can take that information and apply it to your particular application to know, okay, maybe one material is better for me than another. And we also want to incorporate reductions of global warming potential into these. And then finally, we want to reach out to the regional designers within these divisions once we have these user guides to kind of do a lunch and learn session to say, okay, we've produced these, here's what we're looking at. And these are how you would kind of use these and talk with your contractors to try to get these materials used to reduce those global warming potential numbers and emissions numbers down to those target benchmark values based on the strength classifications. And I know we've got questions at the end, but I wanted to throw out my contact information for anyone who has further questions or discussions that they want to reach out to. So thank you.
Hi, everyone. Just a mic check. Can everyone hear me?
Hey, we've got you, Talbot. Thank you.
Great. Thank you all for making it out today. My name is Talbot Ruppel. I'm a research materials engineer here at the Construction Engineering Research Laboratory in Champaign, Illinois. And today I'm going to be speaking to you about mass timber and how it is a sustainable building material for military construction. An outline for this presentation, I'm going to start with the bottom line up front and essentially go into how or why we want to use wood as a resilient building material. And we'll speak about some of its attributes, as well as delving into some of the mission sets of which mass timber can be applied to for the Army. And then I'll go over a couple of examples of mass timber proven in military construction. And then that will bring us into some efforts for the Army to bring mass timber construction and design in-house rather than using a third-party agency to lead the design of a building. And this is through the 6.4 Research Development Technology and Environment Project, Mitigation of Greenhouse Gases in Military Construction Materials. Two direct results of that was a mass timber engineering and construction bulletin, as well as a large technical report focused on concrete, mass timber, and asphalt materials and their sustainability attributes. This will lead us into some relevant criteria and standards related to mass timber, some current early design considerations that have really come to fruition through these pilot projects, as well as delving into some current mass timber EPDs, and then near-term and long-term modernization priorities and research requirements, respectively. So the bottom line up front is that as one of the largest landowners in the world, managing over 550,000 facilities, the DoD needs to bridge the gap between public institution, private industry, and academia to design and develop with renewable lignocellulosic building materials such as wood in pursuit of the Army climate strategy and Army installation strategy goals. And this involves sitting down with experts in the field, in academia, learning from them and working with them, and then being able to translate that into educational materials for our engineers who can then draft and then build with these materials long term. So looking into the Department of the Army policy on resilient building materials, there are three main attributes of what a resilient building material must do. And number one is to maximize the ability of the military to withstand and recover from disruptive events. And this could be extreme weather or disruption to energy and water supplies. Number two, a material must have minimal energy and water demand. Number three, has an indoor environment optimized to promote humans' health and safety. Wood can meet all of these resilient building material criteria in one way or another. It's abundant and regenerative. It's essentially just using wood results in avoided embodied carbon as opposed to if you use alternative materials. Wood is also lightweight. It is reclaimable. It's durable when properly designed with. It's biophilic and improves indoor air quality. It's also aesthetic and offers design flexibility through prefabrication methods. Wood is also 5 times lighter than concrete and 15 times lighter than steel. This dramatically reduces your transportation requirements and your labor requirements on site. And it also costs 20 to 30% less per square foot for 1 to 4 story office buildings compared to counterparts. And really, this is the optimal design criteria and profile for a DoD building. The DoD typically does not build much higher than 4 to 6 stories. And this image on the left shows really just how, or this graph on the left is mass timber projects in the US by year. And as you can see, it's grown exponentially within the past 10 years, and it's only continuing to grow. So applicable mass timber materials. Starting on the left here, we have cross-laminated timber and glue-laminated timber. These two are the most common materials in America for mass timber. And cross-laminated timber is essentially the lumber version of plywood. It is used for floors, walls, and roofs, whereas glue-laminated timber is going to be used for your load-bearing applications for columns and beams and arches. There's also dowel laminated timber, DLT, nail laminated timber, NLT. Mass plywood panels are another very good product that enables the use of wood as a, either a load-bearing application or a spanning application. It essentially can serve as a hybrid product between CLT and glulam. There's also laminated veneer lumber, which is going to be used typically for load-bearing applications for columns and beams, parallel strand lumber, and laminated strand lumber. And essentially what all these products do, mass timber materials, they enable the use of wood for applications which could not be met with traditional dimensional lumber products. It enables the use of wood for larger applications. So the mission sets of which mass timber applies to are forward operating bases, anti-terrorism and force protection, as well as military construction and historic preservation. And today we are focusing on military construction, in which actually 4 cross-laminated timber hotels are operational through the Army via the privatization of Army Lodging Program, which we will discuss now. So mass timber has been proven in MilCon. Back in 2016, the Army funded the construction of the first cross-laminated timber hotel in the United States. However, none of the design was performed in-house. The design was essentially outsourced to Lend-Lease, which is a design build contractor, and they have completed 4 hotels of cross-laminated timber, and they will complete their 6th at Fort Liberty in North Carolina in 2026. The first CLT hotel was the Candlewood Suites at Redstone Arsenal, 2016. Some of the metrics that resulted from this build was that nearly 1 million board feet of lumber was used, and within that wood, 1,200 metric tons of CO2 were stored, and also avoiding about 500 metric tons of CO2 just by using wood over other traditional materials. For a total potential carbon benefit of 1,700 metric tons of CO2 just in this one building. And these are some images directly from the build of that hotel. And I want to go into some more metrics that were a direct result of the Candlewood Suites construction back in 2016. Using CLT construction resulted in a significant waste reduction as compared to a typical concrete and steel structure. It resulted in about 90% reduction in construction traffic, nearly a 45% reduction in labor hours, as well as a 20% faster overall schedule. The average number of employees was nearly cut in half, really because prefabrication methods within the mill take care of and mitigate a lot of the required on-site labor. So the Army wants to be able to design and build with mass timber in-house rather than having to use a third party to lead these efforts. And what that requires is that we educate our engineers, our professional engineers and structural engineers, to be able to build with this new material. Although it's quite not really a new material, but really to the U.S. industry and especially to the DoD, it is. And with this effort came the 6.4 Research and Development Technology and Integration Program titled Mitigation of Greenhouse Gases in Military Construction Materials. And Task 1 involved strategy and coordination. Task 2 involved life cycle assessment of the Task 3 through 5 materials, which were low carbon concrete, timber, and recycled asphalt. And Task 6 was ultimately transition and modernization. And our goals for this project was really to identify low-hanging fruit, unified facilities criteria, and unified facilities guide specifications of which we could implement criteria change requests immediately. And further down the line, we wanted to leverage the expertise of the industry to demonstrate the use of commercially available off-the-shelf materials in a relevant mission set and Army environment. And then thereafter, we wanted to assess the constructability metrics and perform a life cycle assessment on those systems. And this is an ongoing feat in which we plan to have a lot of innovation from this. One direct result of this project back in fiscal year 23 last year was this Mass Timber Engineering and Construction Bulletin titled Mandatory Consideration of Mass Timber in Army MilCon and Civil Works Vertical Construction Projects. And the key takeaways from this excerpt are that project delivery teams must consider at least one mass timber structural solution starting in fiscal year 26 for military construction. And all structural systems considered during design must be documented via a life cycle cost analysis. However, a full life cycle analysis is not required. So a life cycle cost analysis at this point is required, but a life cycle cost assessment is not, or a life cycle assessment is not. Also, ending with a report describing the analyzed structural systems and justifications for non-selection and selection of the primary structural material is required as well. Another direct result of this 6.4 RDT&E program was a technical report titled Unified Facilities Criteria and Unified Facilities Guide Specs for Sustainable MilCon. And this included the concrete, asphalt, wood, and life cycle assessment tasks. And here's just a few of the table of contents directly from the wood product section. This is a very large technical report that's going to be published by the end of this fiscal year. So please keep a lookout for that. Table 14 is an example of some of the things we're looking at, particular to mass timber construction. And a lot of it has to do with integrating updates to the International Building Code, which includes 3 new building types within Type 4 mass timber construction. Previously, the 2018 International Building Code only had heavy timber construction as Type 4. Now Type 4 is broken up into 4 subsections, including heavy timber, Type 4A, Type 4B, and Type 4C construction. And this is and the Type A through C is essentially dependent on the maximum allowable height and number of stories. Some relevant mass timber criterion standards, which we have been assessing, are of course the DoD Building Code, high performance and sustainable building requirements as well, fire protection engineering for facilities, and DoD minimum anti-terrorism standards for buildings. The Unified Facilities Guide specifications, which we're focused on, are really all in Division 6, wood, plastics, and composites. The 2 UFGs are limited to 2 mass timber products, and that's cross-laminated timber and glue-laminated timber. And various updates are required and needed for those UFGs. And a lot of these updates will come directly from the International Building Code Industry Standard 2021. Some other industry standards which we are considering and play a major role in the design of these buildings are the special design provisions for wind and seismic. This is particularly important in Class 4 and Class 5 environmental severity classification regions. And this is really coastal regions in which, wood, cross-laminated timber, engineered wood should really not be exposed to the elements in those regions. There's some extra cautions that need to be used when building in those regions, and some restrictions in which CLT shear walls, and for instance, cannot be used to some extent. There's also product standards for glue laminated timber, as well as the adhesives used for these materials. Some mass timber design considerations that we have found early on, from these, speaking to engineers that are involved in these pilot projects, and one of the pilot projects is the JBLM barracks out in Tacoma, Washington. These pilot projects will be discussed much further in detail next week. But really, upfront planning has proven to be very important within mass timber construction. There's a lot of building information management coordination that must happen between manufacturers, designers, as well as builders. There are also some conflicting sustainability versus anti-terrorism and force protection requirements. For example, sustainability efforts call for essentially having larger windows to enable natural sunlight to enter the room for natural heating and ventilation. However, ATFP requirements call for smaller windows to prevent any chance of projectiles entering. Another example is standoff distances, where ATFP wants maximum standoff distances, whereas sustainability efforts, really see those standoff distances as minimizing connectivity within the workplace or the living space, whatever the building is. There's also some considerations regarding the 90%, the 90 square foot per service member and the minimum number of beds. Because these are lignocellulosic building materials, they do not, they require essentially a larger section of walls and building sections. So this somewhat reduces the available square footage within the interior of the building. So that means that proper planning and design ahead of time must be considered to meet those minimum square footage requirements. Some other contingencies are reaching minimum R value requirements, panel aspect ratios, particularly important to the special design provisions for wind and seismic, as well as acoustic requirements, design load capacities, mechanical, electrical, and plumbing requirements and routing, as well as fire rating requirements for structural members and fasteners, and window spacing too. Some of the current mass timber environmental product declarations, I found this information from buildingtransparency.org. For cross-laminated timber, there are 21 environmental product declarations. Only 2 of those are from American-based companies. And for industry environmental product declarations, there are 20 of them. However, none are US-based. They're all either Australia or Canada or New Zealand. But the average kilograms of CO2 is about 76 for cross-laminated timber, and glue laminated timber is about 78. And it's quite a similar story with glue lam. There's 12 environmental product declarations, none of which for glue laminated timber, or actually, I'm sorry, 2 of those of glue laminated timber are from US-based companies. For industry product EPDs, there are none that are US-based. So really the US industry has some work to do to as well integrate that information into these open source building transparency websites. Mass plywood panels has a little bit higher embodied carbon as compared to cross-laminated timber and glue laminated timber. And that's because more petroleum derived glue is used in these panels. They're also more dense. So in the mass plywood industry, there's a big focus on reducing the amount of resin, especially petrol-derived resins, required for these composites. And there's a big push for utilizing bio-based adhesives. Some near-term modernization priorities for mass timber in Army construction are to optimize the material strength and durability with novel treatments and finishing solutions. We want to demonstrate commercial off-the-shelf occupiable components and systems in DoD applications. We know that in the industry, this product being widely utilized. So there's no reason why the DoD should not be using these materials. We want to make these materials and systems lightweight, modular, and designed for disassembly, and ultimately to deliver relevant criteria change requests to streamline the use of these materials for our engineers in the field. And we also want to assess the building construction efficiency and building envelope performance metrics as compared to traditional materials, as well as perform life cycle cost assessments. And there's also a mission set, which is not directly related to mass timber materials specifically. This is more for wood packaging materials, but mold mitigation is a very big issue, particularly for the Joint Munitions Command. And all of the innovations that stem from this problem set of mold mitigation can be implemented to larger structural components like mass timber and building systems. Some long-term research requirements for mass timber are really to adopt environmental product declarations that are widely utilized in the industry, and really coincide with the growth of the industry in terms of knowledge and implementation, and learning from Woodworks, who is the largest design and consulting firm in the U.S., nonprofit organization that assists with all mass timber projects in the U.S. We want to advance our biomaterial strategic sourcing, design, and construction. On the bottom left, we have a map of our mass timber manufacturing facilities in North America. About a quarter of those are all in Oregon. However, the number of manufacturing facilities is slowly growing. However, there's quite a big gap, especially in the Midwest, where there's not as much trees. So there's some logistical obstacles that need to be met. However, it's been found that the transportation cost for wood versus other more dense materials is a fraction of the cost, and wood can be shipped over much longer distances than traditional materials at a fraction of the cost. So that there should be some relevance there in terms of the lightweight nature of wood. And also we want to perform some research in lateral load optimization for CLT shear walls, which have been a limitation in these regions, C4 and C5, as well as seismic regions. And we want to optimize our anti-terrorism and force protection metrics for these materials, optimize acoustics, as well as enhance building information modeling coordination systems. And so that's all from me today. I want to thank you all for your time. Again, my name is Talbot Ruppel, research materials engineer. Thank you to Megan and Jerry for starting this presentation. And I want to say thank you, Stephanie, as well as Ed Sitzler for giving us this opportunity. So thank you, guys. I'll leave this open to questions.
Yeah, it was our pleasure. Thanks so much. I appreciate that. We do have one question in the chat. You mentioned about coordinating with timber manufacturers early in the project. Have you run into proprietary issues when using a specific product for Army construction?
Sorry, we have not ran into to any proprietary issues regarding layup of the composites at this. However, I think once the composite reaches a certain design stage, especially when they're interacting with field engineers, there does some CUI does come up, but at this point it's pretty the layups are pretty universal. There's not a whole lot of claims that companies can make with some of these materials unless they're using a certain additive within their adhesive or coating system. One thing that we're actively working on at Searle and researching is thermal modification of wood. And thermal modification it's not a new process. It's essentially pyrolysis of the wood. So baking the wood in the absence of oxygen. And there's some manufacturers that are, exploring this possibility. But even that, if they were to come out and say their cross-laminated timber has thermally modified benefits, they wouldn't be able to claim that as a patent or anything like that. But we have not faced any of those issues quite yet.
Okay. We have
Dalton,
one more
I got
here.
a question for you.
There you go.
Yeah, of course.
So, but also we partner with Woodworks. This is Ed, by the way. We partner also with Woodworks, which is a nonprofit, and also a opportunity to collect information. Is that pretty accurate?
Yes, sir.
Yeah. So they're they're a good source for information and details and all that. With since they're nonprofit, they're non-proprietary also. That's what I would like to add too.
Of course. And we I can't say the details of the contract, but we have put mechanisms in place to be able to interact freely with Woodworks over the next several years, as well as the Forest Products Laboratory, in implementing and for design assistance regarding these pilot projects. So a lot of work has been done behind the scenes to solidify these relationships with these industry and other federal organizations like the Forest Products Laboratory.
Excellent. Just jumping in, there's another one. I like to read these out just for the folks that are on the call. Will our criteria codes include requirements and oversight for responsible harvesting and replanting to ensure we aren't continuing to degrade habitat in ways that reduce the biodiversity over large swaths of natural habitat as mass timber construction is adopted?
Of course, I definitely think that there needs to be an excerpt, that was not actually in the cross-laminated timber or the glue laminated construction UFGs. And I think there should be a section which explains that any of the wood utilized is from is either SFI Sustainable Forestry Initiative certified or Forest Stewardship Certification FSC certified. I think those are two of the two primary certification mechanisms in the U.S. To meet that LEED status and to lead to the LEED Silver certification. But yeah, that's definitely something that's not as much talked about when it comes to designing with these materials, is also the impact that it does have on the environment and wildlife. And obviously we don't want monoculture plantations of trees, but we also don't want to cut down old forests. So there has to be a happy medium between forest stewardship and harvesting these materials for building applications. Stephanie, I think you're muted.
Good Lord, rookie mistake. All right, let's
No
try
worries.
again. From Brian Rundgren, there have been a number of high-profile massive fires of mass timber buildings that were under construction. Is there any work being done on examining our construction safety requirements? Do you know of anything that you could add to that?
I have not. I personally haven't heard of these fires with mass timber But their mass timber and engineered wood products in general have very different burning characteristics than traditional dimensional lumber. These materials char on the outside when exposed to fire, and they have to meet stringent fire safety requirements. Typically, a minimum of 2-hour fire rating is required for type 4 buildings. So there's a lot of research going on that has to do with not only the exposed interior of the wood members within the building, but also the connections and the fire ratings of those connections that go with that go along with it. So yeah, I'd be curious to learn more about any of those fire issues that have been faced. But they're definitely there will be a big section actually in this technical report that will be published in the next couple of months that will have to do with fire rating. And a lot of it comes directly from the 2021 International Building Code. But at this point, I personally have not heard of those fires in timber buildings.
Yeah, from what I understand, they typically perform really well. In that they do just, it seems that they perform differently than steel and your typical construction. All right, so listen, mass timber is definitely having a moment right now, no doubt. But we also had 2 other fabulous presentations. I'm endlessly fascinated by concrete. Can't explain it, but I am. And also we had a great presentation from Megan Fuller about embodied carbon. Does anybody have any questions for them? We've got Billy Tyndall asking for references on the high-profile massive fires. So maybe we'll get more information about that. But in the meantime, does anybody have any questions for Megan Fuller or Dr. Jerry Paris? All right, not hearing any. Really appreciate it, Megan, Dr. Paris, and Talbot. Really appreciate your time. This has been great. I feel like you all brought a lot of information to us today. I really appreciate it. If there's any other questions, you guys can reach out. Obviously, you have their information. It's in the meeting invite, so you can reach out with any questions. But for now, thank you very much. We'll see you next week. Thanks a lot. Bye-bye.
Take care, everyone. Have a great day.
Thanks. Bye.